Sylvia Miss, the time now is 2:30. Shall we start?
Yes, we can start.
Okay. Go down deep enough into anything and you will find mathematics. Good afternoon, one and all. A warm welcome to today's webinar on singular value decomposition, organized by the Department of Mathematics and IQAC of Fatima Mother National College, Kollam. First of all, let us bow our heads before the Lord Almighty, invoking His blessings. Thank you all. I request Dr. Roshni B., Assistant Professor in Mathematics of our college, to welcome everyone to this webinar. Roshni, please.
Thank you, Miss. Today, we have an eminent resource person, Dr. V.B. Kiran Kumar sir, for our webinar on singular value decomposition. A warm welcome to you, sir. I also welcome all other participants from various colleges, our students or colleagues to this section. Thank you.
Thank you, Roshni. May I now invite Professor Sylvia Anthony, Head of the Department of Mathematics of our college, to introduce the resource person, Dr. V.B. Kiran Kumar, Assistant Professor, Department of Mathematics, QSAT. Over to you, Miss.
Hello. I'm very happy to introduce Dr. B.B. Kiran Kumar, Assistant Professor, Department of Mathematics, QSAT. Dr. Kiran Kumar is actually a native of Kozhikode district, but presently he is residing at Kochi. He did his bachelor's degree in University of Calicut and his master's in University of Cochin and University at QSAT. And his versatility is evident from the fact that he has got many research scholars under him. Also, he has got many publications and presentations to his credit. I'm sure that at the end of this seminar, we will all be a bit more mathematically wiser. Thank you.
Thank you, Miss. Participants, please note, you can post your queries in the chat box in between the presentation. These questions will be discussed at the end of the presentation. Feedback link will be posted in chat box for Zoom participants and comment box for YouTube participants. Please fill up the form correctly. You will get system generated participation certificates in your mail ID. Now we are moving on to the main part of this webinar. I am indeed happy to have Dr. Kiran sir as a resource person today, who is following the legacy of Dr. M.N. Nambudiri, an eminent mathematician in QSAT, the research guide of a resource person. Dr. Kiran is the recipient of Kerala State Young Scientist Award 2017 of Kerala State Council for Science, Technology and Environment. He has got an UGC Startup Research Grant of Rs 10 lakhs and National Board of Higher Mathematics Postdoctoral Fellowship. I am proud to say that he was my MSc classmate at QSAT. May I request Dr. Kiran Kumar sir to take over the session. Over to you, sir.
Yeah, so can you hear me?
Yes, yes.
Okay, thank you, Ann. So let me share my screen first. So it says that I don't have permission to share my screen.
Now you can share, sir. It's okay now.
Oh, okay, thank you. Okay, so I guess all of you can see my slides and
yes, sir.
hear my voice.
Fine, sir.
Okay, so so today's topic is singular value decomposition. So this is a topic which has been used in wide variety of areas, and nowadays in the era of data science and machine learning, it found its new realm of applications, and it keeps going on improving this area. So, but things started from an elementary linear algebraic problems and so on. So this talk will be quite elementary in nature. I hope I'm audible, right?
Yes, yes, sir.
Yes, sir.
Okay. So this talk is going to be very elementary in nature. I will not assume much of the background, except some operation, matrix operations and so on. Okay. So let me begin with some geometrical ideas regarding the linear maps. Okay. So we will consider linear maps acting between finite dimensional vector spaces, and all the vector spaces we consider assumed to be over C or R. Okay. So if some of you are not familiar with the definition, let me tell you that linear maps are those maps which preserve the structure of a vector space, and that means it preserves addition and scalar multiplication. You can see that A is a map which sends A of x plus y to ax plus ay, and A of scalar multiplication goes to C comes outside. I mean, the scalar will come outside. Okay. So again, if some of you are not comfortable with the notion of linear transformations, you can think about a matrix. So matrix is something familiar to most of you. So you consider a square matrix or a rectangular matrix of order m by n, and you treat it as a map from say Cm to Cn to Cm by left multiplication by the matrix. Okay. So in finite dimensional case, the matrices or linear transformations are equivalent in some sense. So if you have a linear transformation on finite dimensional space, fixing a basis, you can find a matrix, and you can do the other way also. If you have a matrix by left multiplication, it will generate a linear transformation. So those who are comfortable with linear transformations can consider this, or if you are not comfortable with that, then just imagine that I am talking about a matrix, okay, m by n matrix. Okay. Now let me just introduce a couple of geometric properties of a linear transformation. So a linear transformation will map lines into lines and parallel lines into parallel lines. It will preserve parallels. So let us prove this elementary fact using linearity, simple linearity. Yeah, look at here. So consider a line L passing through a point P. So maybe in the direction of some vector R. So you have the parameterized equation to be P line. This is the parametric equation. So it passed through P. So it is P plus TR, where T varying over R. So it's a line passing through P in the direction of R. Now, if you apply A to this line, then what happens? By linearity, it will go to A of P plus T is a scalar, so T will come outside A of R. So it will become a line. Again, it's an equation of a line. It's a line passing through the point A of P. So it tells you that a linear transformation will transform lines into lines. Similarly, you will get that the property of being parallel is preserved under linear transformation. That's also easy because the direction of the line is determined by this vector R. So if you consider two vectors in this with the same direction, I mean, it can be of opposite direction also, but this R could be same because I am running T over the whole real line, so it's fine. So suppose L1 is P1 plus TR and L2 is P2 plus TR. So this represents two parallel lines, one passing through P1 and the second passing through P2. Now you apply A to these two lines. So what is the image of these lines under A? So that is AP1 plus T into AR, and again AP2 plus T into AR. This is the parameterized equation of the image. So then what happens? They are having this AR, same AR here, same direction. So that means these two lines are parallel. So I wanted to tell you this because most of the time when we deal with the linear algebraic thing, the geometry is missing most of the time. So let us see that most of the linear transformation enjoys certain geometric property. So this is to begin with. So next thing is we will consider some other examples of linear transformations which are of geometrically high importance. So they are called rotations and reflections. So let us consider what is a rotation. So just consider the two-dimensional plane and look at the map which sends a vector rotated through an angle theta. So what happens? A vector is rotated through an angle theta. So you define it as a map. That means every vector is rotated through an angle theta, but theta is fixed. Then this will define a linear transformation on Earth. Now, as I mentioned earlier, every linear transformation on a finite Earth space, you can compute the basis, compute the metrics associated with that by fixing a basis. So let us consider the standard basis 1, 0, and 0, 1. So how do you compute that matrix? You just consider the action of this linear transformation on these basis elements. That's the way in which we compute the matrix, associated matrix. Okay. Now let us see what happens to the vector E1 or 1, 0 when it is rotated through an angle theta. So this is a pictorial representation. Yeah. So this line is E1. Now you assume that it is rotated through an angle theta. So this is the image of that. So this is the image of 1, 0 under a rotation by an angle theta. Then you compute the coefficients here. I mean, at this point, you can see that this line has length 1 itself, because what we rotate, rotation will not alter the length. Okay, so we are just rotating it. It is the same. It is of the same length. So since this is of length 1, you can see that, and this angle is theta. You can see that cos theta will give you this x coordinate by 1, and cosine theta will give you y coordinate by 1. In other words, this point will be cos theta sine theta. This point. So a of 1, 0 will be cos theta sine theta, which you can write as cos theta into 1, 0 plus sine theta into 0, 1. Therefore, the first column is cos theta sine theta. Similarly, you can compute the second column by looking at the action of a at 0, 1, at the vector 0, 1. So that you will get minus sine theta cos theta. So what happens is that rotation by an angle will have this matrix representation. This is one linear transformation which with some geometric significance. Another one is reflection. So let us consider, reflection can be considered with respect to any line or even in general any curve. But we consider reflection with respect to the real axis. Okay. Then again, doing the same process, you will obtain that the matrix is represented by 1, 0 and 0 minus 1. Because reflection with respect to x-axis will fix the vector 1, 0. That will not be going anywhere, because we are that lying on the real line. So by reflecting with respect to the real line, that will be fixed. So 1, 0 will go to 1, 0 itself, and 0, 1 will go to 0 minus 1. That's why you are having this minus sign. So reflection will be this. Now, what is the important is that you consider these two matrices or operators. These two transformations enjoy a very important property, something called the orthogonality. I mean, you take transpose of the matrix, so then A transpose will be identity, and the same thing will hold for A transpose A. So it satisfies that A transpose equal to identity equal to A transpose A. But A transpose is the transpose of the matrix which you are familiar. So we have seen that any rotation or reflection will satisfy this property. Now let us look at the converse. In fact, converse is also true. So what is the converse? You start from a matrix on R2, I mean 2 by 2 matrix, which satisfies this property. A transpose equal to identity equal to A transpose A. Then we can actually show that this matrix will be a combination of rotation and reflection. Let us see the proof now. Yeah. So we have A transpose equal to identity equal to A transpose A. So then what happens? You consider the you know that 1, 0 will be mapped onto some element by A. So you look at the image of 1, 0, the vector 1, 0 under the given transformation A. That means A of 1, 0. and you consider the angle between them, 1, 0 and the image of 1, 0 under A. So you call it theta. And let R denote the rotation by this angle theta. Now you consider B equal to R inverse A. Again, one point you should keep in your mind that rotations are always invertible. That is quite evident from geometry itself. If you can rotate by angle theta, you can rotate by an angle minus theta also. You can reach back. That is one thing. Another thing is that the matrix which represents the rotation is, this matrix has a determinant plus this matrix has determinant 1. So that is another reason why it is invertible. So now what happens is that you consider this matrix, this operator or matrix B equal to R inverse A. Now what happens to 1, 0? So now we are going to, you know that R inverse is a transformation, A is a transformation, their composition is again another transformation on R2. Now we are going to compute the matrix associated with this transformation. Again, we compute the action on the basis elements 1, 0 and 0, 1. So for 1, 0, what happens? If you apply 1, 0, first you act A, it will go to A of 1, 0. Then you are considering R inverse. See that R is a rotation which rotates 1, 0 to A of 1, 0. So R inverse will rotate A of 1, 0 to 1, 0. So what happens that 1, 0 will be fixed by this matrix, this operator B. So 1, 0 is fixed, therefore the first column will be this 1, 0 itself. Okay. Now again you can actually verify that B transpose equal to identity equal to B transpose B. And this will tell you that the matrix has determinant plus or minus 1. Because determinant, you compute determinant of both sides. So determinant has the property that determinant of the product is product of the determinant once you are dealing with this square matrix kind of thing. So determinant B into determinant B transpose is 1. Therefore, and determinant of B transpose is same as determinant B. So what happens is that determinant B will be either 1 or minus 1. So that is another reason, another thing which you have to observe. Another one is that once you have this property, B transpose equal to identity, that will tell you that this the entry here should be 0. Otherwise, this will not satisfy. You can just compute. I mean, that is obtained by computation. So this is 0. This can be any number. B can be any number, but with this determinant criteria, B can be either minus 1 or plus 1 because this matrix will have determinant B. So that means B is equal to 1 minus 1 0 0 here or the identity matrix. Now from this identity we know that A is equal to R into B. So you know that A equal to R into B. If B is identity, A equal to R, it's a rotation. If B is 1 minus 1, that means reflection. Then A is a combination of rotation and reflection. That completes the proof. So this tells you that if you have an orthogonal transformation on R2, in fact, you can do the same thing on R3 also. I'm not proving it here. It will be a combination of rotation and reflections. Now, what happens to diagonal matrices? Diagonal matrix also has the same similar geometrical property. It's a kind of scaling. So if you consider 2 by 2 diagonal matrix A 0 0 B, what happens? The action is like this. X5 will be mapped onto AX B1. That means the vector is scaled to this AB. So that is the geometry of diagonal matrices. You can also see. Now what we are going to do, single value decomposition will tell you that any transformation on R2 or R3 is a combination of rotations, reflections, and scaling. These are all. Okay. You take any linear transformation, you can find it as a combination of these 3 kind of transformations. In other words, it will characterize all linear transformations here. Now, before stating singular value decomposition, let me fix my notation. So all of you are familiar with transpose of a matrix. I will also consider A star. A star as a matrix, A star by A star, I mean conjugate transpose. Take the transpose and take the conjugate of each element. That's all. But once you are dealing with real matrices, I mean real matrices with real entries, then it is the same as taking transpose. So conjugation will not have any effect. So this is the idea. So A star means you take conjugate transpose. Okay. Now here is a singular value decomposition. So it tells you that We start from a m by n rectangular matrix with real or complex entries. Then A can be written as U D V star. So any m by n matrix has the can be written as a composition of three matrices. And what are the properties of these three matrices? The middle one, as the notation indicates, it's something like a diagonal matrix. It is not, strictly speaking, it's not diagonal. The middle one D will have this property. I mean, this structure. It will be, there will be a diagonal matrix. So suppose m greater than n, then it will be a diagonal matrix here, and some remaining part you have 0 rows will be 0. And if m less than n, then diagonal matrix will lie here, and you will have 0 on the some 0 columns on the right side. So this middle term D will be something like a diagonal matrix, or D1 and 0 diagonal and some zeros in addition. If m equal to n, there is a diagonal matrix. Now, what about U and V star? They are orthogonal. In fact, they are unitary matrices. So U and V are square matrices, and they satisfy this property. U star equal to identical U star U, V star equal to identical to V star V. And if you reduce to real case, V star and U star are transposed only. Then what happens? You are getting that. So you are getting that any matrix is a composition of rotation, reflection, or scaling. That's what we are getting. Okay. So U and V are simply rotations or combination of rotations and reflections. So this is a singular value decomposition for you. Now, one more comment I wish to make. Yeah. So here you look at D. D is of this form. It is a diagonal matrix with some additional rows as zeros, or a diagonal matrix here and some additional zeros on the as columns. Now look at the diagonal matrix. The diagonal entries are sigma 1, sigma 2, etc., sigma n. They should be non-negative. Okay. So this is the picture of single value decomposition. So now we are going to see its geometrical interpretation. What does it mean by geometrical? Let us consider simple 2 by 2 case, and let us consider real case. Okay. Suppose A is a 2 by 2 invertible matrix with real entries. Okay. Now, what is singular value decomposition now? I denote it in short SVD. So you have SVD A equal to U D V transpose. So remember, we are dealing with the real matrices. Therefore, you don't have star here. Instead, you have transpose only. You don't have to take the conjugate. So A is equal to U D V transpose, and U transpose is identity, and V transpose is also identity. And this is 2 by 2 case. Therefore, this U and V are, as we have noticed just before, they are orthogonal matrices. Therefore, they are combinations of rotations and reflections. Okay. And now D is sigma 1, sigma 2 on the diagonal and 0 x. Okay. Now remember, we have started with an invertible matrix. So any invertible matrix has determinant non-zero. Okay. So determinant A equal to non-zero. And if you look at here, if you compute this determinant here, that means determinant of A is this, determinant of U into determinant of D. So again, determinant of product is product of determinant. That will tell you that determinant of D should be non-zero. But determinant of D is sigma 1 into sigma 2. So that is non-zero, means sigma 2 should be strictly greater than 0. So here you have sigma 1 and sigma 2 strictly greater than 0. It follows the order. Okay. Now let us find out the image of the unit circle, say S, under this linear transformation A. So suppose S is the unit circle. What is the unit circle? Unit circle is analytically you can have this expression. Set up all a ordered pair with x square plus y square equal to 1. Unit circle the center at the origin. Now we are going to find out the image of S under this map. So image is A xy is U D V transpose acting at x. Now look at here. First action will be of V transpose, but we know that V transpose is a combination. It's a matrix which satisfies this identity. Therefore, V transpose is a combination of rotation and reflection. So what happens rotation of a unit circle? If a unit circle is rotated, nothing will change. Okay, it will remain as a unit circle itself. Now, what happens? It's reflection with respect to real line. This is a unit circle centered at origin. So, if you reflect it with respect to origin, with respect to the real line, it will remain as a unit circle, same. So, no effect will be there. So, V transpose keeps the unit circle rotated and reflected, but it will not go beyond the unit circle. So, the image will be unit circle itself. Okay. Now, the next action is by D. So, V transpose is already acted. Now, D. What is the action of D here? It's a scaling. D of xy will be sigma 1x and sigma 2y. If you call it uv, then you can see that u by sigma 1 is x and v by sigma 2 is y. We can do that because sigma 1 and sigma 2 are non-zero. Therefore, u square by sigma 1 square plus v square by sigma 2 square equal to x square plus y square. But x and y, xy comes from the unit circle, that is equal to 1. That means image under D is this. And what is this? This is the equation of an ellipse. So u square by sigma 1 square plus v square by sigma 2 square equal to 1. This is the equation of an ellipse. And this is the action of D. So now, if by the action of D, what happens? Your unit circle is structured as an ellipse now. Now again you apply U. U is again a combination of rotation or reflection. So that will not change much. So it will be simply rotating or reflecting. So it will not change the structure. It will only just rotate the ellipse and it will remain as an ellipse. And if you reflect it, then also it will remain as an ellipse. No change in the geometrical figure. So this is what happens. So first action of V transpose will simply rotate or reflect this unit circle and it will not make any change. But if you apply the D, then it will stretch this unit circle as an ellipse like this. Now, again, the second action of U will simply rotate or maybe reflect if you want. So that's what happens. Okay. And this ellipse has the equation that u square by sigma 1 square plus v square by sigma 2 square equal to 1. So sigma 1 and sigma 2 represent the magnitude of the semi-axis of this ellipse. So this is the geometrical illustration of singular value decomposition. Now these numbers sigma 1, sigma 2, etc., sigma m appearing in this SVD are called the singular values of A. Now it is not that difficult to compute these values. In fact, you don't have to obtain singular value decomposition to obtain singular values. So the simplest method to compute singular values is you just consider the matrix A star A. You can just you can simply take conjugate transpose and compute A star and multiply it with A. Then what happens? A star A has the property that it's all its eigenvalues will be non-negative, so that you can take positive square roots of them, and there will be exactly these numbers, singular values. So you can compute in this way also. Now, finally, in general SVD, we will give you A equal to U D V transpose, and you know that these three transformations appearing in this SVD are geometrically evident. What are they? We know what are they, because they breaks down it into these transformations, rotations, reflections, and scaling. So in the precise order, first we will rotate or reflect, and then the scaling, and then again followed by a rotation or reflection. So this is the geometric illustration of singular value decomposition. Now we have introduced singular value decomposition. Now we are going to see certain applications. Okay, why this singular value decomposition is important? Where are this objective? Where are it is being applied? So we will see some kind of applications. The most important application of singular value decomposition is in solving system of linear equations. So system of linear equations arise quite naturally from the physical phenomena, and we should have some method to solve that. Okay, and usually what happens if you have a system of linear equations represented by some matrix, say Ax equal to B. If you have this matrix A invertible, then the solution is uniquely determined by A inverse B. So X is exactly A inverse B. That is a solution. There are no other solution. It's a unique solution and things are fine. But this is not the situation in most of the practical phenomena. A solution need not exist. Even though the solution exists, that need not be unique. Even though there is a unique solution, that need not be computable. So there are several problems which arise when you deal with system of linear equations. Especially when you deal with a rectangular system. That means if you are dealing with m equations in n unknowns, with m and n are different, then corresponding structure will not have a square matrix. Instead, you will have a rectangular matrix. So there is no point of invertibility there. So in all those situations, inverse will not help you. So you need something which behaves like an inverse, or which does all the purpose of an inverse, but even though the inverse does not exist, even in that situation. So that is something we call pseudo inverse, and it is also called Moore-Penrose inverse. This name Penrose is familiar to you. It is attributed to Roger Penrose. He won the Nobel Prize very recently. Last month it was announced for his studies on some singularities related with black holes and all. Of course, he is a physicist, and that itself tells you that why this Moore-Penrose, why this kind of inverse and all other things are relevant in the physical point of view. Now let me introduce this Moore-Penrose inverse or pseudo inverse in an axiomatic way, and later we will see how it can be computed and so on. Okay, you begin with the m by n matrix A with real or complex entries. Then the pseudo inverse or Moore-Penrose inverse of A, you call it A dagger. It is called A dagger. So it is a unique matrix which satisfies these four conditions. Okay. So what are these four conditions? Let us have a look at it. A dagger A should be A dagger A dagger should be A dagger. And last couple of conditions will tell you that A dagger and A dagger A are adjoint of themselves, or self-adjoint, or Hermitian in other words. Okay. Let us look at the first condition. Suppose if A is a square matrix and A inverse exists, then you replace A dagger by A inverse, then this will be automatically satisfied, because if A inverse comes here, this quantity become identity and you have A equal to A. And this is also satisfied because A inverse comes here means this becomes identity and A dagger equal to A. And this is also trivially satisfied because A dagger A inverse comes here means this is identity. These are identity matrices. So identity matrix, if you take conjugate transpose, you get identity matrices. So you can see that these are the properties enjoyed trivially by the inverse of a matrix, but this is much general because even this exists in situations where inverse does not exist. Okay, so I defined it to be a unique matrix satisfying such a thing, but I did not prove the existence and uniqueness. I will come to that, but I just observed that if A inverse exists, then all these actions are satisfied and we get A dagger equal to A inverse. By uniqueness, we will prove the uniqueness. And I just want to make a couple of comments about the last couple of properties. Yeah, it tells you that A dagger star is equal to A dagger. That means its adjoint is that itself. Such a matrix is called Hermitian. Okay, so it tells you that A dagger is a Hermitian matrix. Similarly, A dagger A is also a Hermitian matrix. But in fact, it tells you something more. You compute A dagger square. You take the square of this matrix. Then what happens? It is A dagger multiplied with A dagger. But you use the first property. So first three things will reduce to A itself. So what you will be ending up with A dagger itself. That means A dagger square will be A dagger itself. Similarly, A dagger A square will be A dagger A itself. That means they are all matrices satisfying P equal to P square equal to P star. And such matrices are called orthogonal projections. And they enjoy certain kind of geometric properties. In fact, in the much general situation also, they are meaningful. But let me not comment on that, but I will use some geometry property of this at a later stage. So, but keep in your mind that these are this A dagger and A dagger A are matrices which satisfy this property. P equal to P square equal to P star. Okay. Now the question of existence and uniqueness. Does there exist a pseudo inverse or Moore-Penrose inverse corresponding to every n by n matrix? And if it exists, whether it is unique. We prove uniqueness first and we'll come to existence later. So suppose, so as usual, we prove uniqueness by assuming that there are two and we'll prove that these two are equal. Okay. Suppose A dagger and B dagger, two matrices satisfying 1 to 4 corresponding to A. That means all the properties, all these four properties are satisfied by A dagger as well as B dagger. And later we will prove that A dagger equal to B. Does there actually a question? Do you have a question?
Sir, interactive session will be at the end.
Okay, so I hear some sound. That's it. Okay.
Okay.
Okay. So so let me prove uniqueness by this. So you assume that there are two, like A dagger and B dagger. Now you prove this. So consider A dagger. Now A can be replaced by A B dagger A by property 1 because B dagger enjoys property 1 to 4. So A B dagger A should be A. So this is what you can do. Now you just use associativity and write this A B dagger A dagger. Now A B dagger will be equal to A B dagger star by property 3 and A dagger will be A dagger star by property 3. So now you use the property of the adjoint operation that AB all star will be B star A star, just like the transpose. So you will obtain this. Okay. Now what happens? You take them together, the last three together. That is actually A dagger A all star. Now A dagger A is A by property 1. So that is A star B dagger star A star. Now this is again, this is A B dagger all star. Okay. So what happens? You obtain that this is A B dagger all star. But again by property 3, A B dagger all star is A B dagger itself. So what happens? You obtain A dagger equal to A B dagger. So that's what we get. Okay. In a similar computation, you will obtain A dagger A equal to B dagger A. Okay. Now we are going to prove that A dagger equal to B dagger. You begin with A dagger, and by property 2, this is the property 2. Yeah. A dagger is equal to A dagger A dagger. So property 2 will tell you that A dagger can be written as this. Now here we take A dagger together. We have proved that A dagger is A B dagger. So you replace it by A B dagger, last two things. And now you take this together, first two matrices together, that is A dagger A. And we proved that A dagger A is B dagger A. So you replace it by B dagger A. So now we get B dagger A B dagger. But by property 2, it is B dagger. So we obtain that A dagger equal to B dagger. So this is a simple proof of uniqueness. That is easy to prove. We have only used the algebraic identities. That is easy. And the matrix property of associate matrix multiplication is associative and so on. Now regarding existence. Existence, in fact, for every real or complex matrices, A dagger exists. But we will not prove it directly. Instead, we will give a method to compute the A dagger corresponding to every real or complex matrices. But before that, we need this. We start from a scalar x belongs to R or C. How do you define x dagger? Dagger for the scalar. That is defined to be 1 by x if x is non-zero and 0 otherwise. And you can see that with you treat x as a scalar, the scalar as a 1 by 1 matrix. So you can see that this x dagger will satisfy all the properties 1 to 4. That is very easy because it is just like inverse of x. But when x equals 0, you have 0 everywhere. So these are trivially satisfied. So this is x dagger for a scalar, a real or complex number. Okay. So in general, we will not prove the existence of the A dagger for an arbitrary matrix. Instead, we will provide an explicit method to compute A dagger. That's where singular value decomposition comes into picture. Yeah. Now look at a diagonal matrix. Suppose D is a diagonal matrix like this. Then you can easily see that if you define D dagger to be this, I mean, you replace every diagonal entry by its dagger. Sigma 1, you replace by sigma 1 dagger. That means if sigma 1 is not 0, it is 1 by sigma 1, otherwise it is 0. You put 0 there. So if you replace like that, then it is an easy exercise to prove that this D dagger satisfies all the property 1 to 4 for D. That means for a diagonal matrix, it is straightforward to compute the inverse, I mean, pseudo inverse or Moore-Penrose inverse. That is straightforward. You just replace the diagonal entries by its reciprocal if it is not 0, or put 0 if they are 0. Okay. So that is easy. Now for diagonal matrix, you are done. Now suppose your matrix is of this form, a diagonal here and some 0 columns on the right. Then you put D dagger to be D1 dagger. D1 dagger you can compute because D1 is diagonal. You can compute in this way and put as many columns, zeros, as many columns here. So how many zeros here? That many zeros you put here as rows. So you can prove that D dagger can be computed if D is of this form. Similarly, if D is of this form, diagonal here and some additional rows, 0 rows, then you can put it like this. Okay. So it's an exercise for you, which you can easily compute to verify that the properties 1 to 4 are satisfied. It is easy because we are dealing with the diagonal matrices only. Okay. Now, using this, we use singular value decomposition to compute the Moore-Penrose inverse of an arbitrary matrix, arbitrary n by n matrix. So that is the first application of singular value decomposition, which is mentioned today. So recall that for a n by n matrix, this is a singular value decomposition. A can be written as U, D, V star, where U and V satisfy these identities. They are unitary matrices, and D is a matrix of this form, either D10 or D10 like this. So D is a matrix of this kind. Okay, it is diagonal, and you know how to compute the D dagger. So that's the advantage here. Now, with direct computation, one can prove that A dagger is obtained by this V D dagger U star. It's a simple matrix multiplication. You can just verify this. So put A dagger to be this and verify that the property 1 to 4 is satisfied. So you proved existence, and already you have proved uniqueness. Therefore, there are no other choice. So this is the first application of singular value decomposition. It gives a direct method to compute the pseudo inverse. So in fact, there are several algorithms available to compute the singular value decomposition. Okay, so there are several other, especially the one by Gulab and Rinch was much popular, and it was it was also considered by people like Tony Chan and Arad Chan. So there are several such efficient algorithms are available to compute singular value decomposition. So once you are able to compute the singular value decomposition, then using this technique, it is easy to compute the Moore-Penrose inverse. Okay, and this is computationally simple and accurate. Now to move further and to discuss further applications of singular value decomposition, I need some geometric structure on Zn. If some of you are not familiar with this, then just imagine the dot product. That's all. So this is just like dot product. So you start from Zn, and Zn is simply the n tuples of complex numbers. And on Zn, let me denote the inner product Zw by this summation j equal to 1 to n Zj bar Wj. And most of the mathematical textbook, the bar, the conjugate will come in the second entry. But that will not create any problem, unless the fact that here I will have linearity on the second variable. If you assume bar here, linearity will be on the first variable. So these are some properties enjoyed by this inner product. In fact, if you are not comfortable with this, just imagine that I have a dot product there, and from dot product I can obtain S. From the dot product I can obtain the absolute value square by taking A dot A. I have the same thing here. Taking inner product ZZ, I have something non-negative, and I can take the square root of that. So that is how do you obtain the Euclidean norm, which is denoted by norm x2 is equal to summation mod xj square all power 1 by 2. So this norm is induced by the inner product. In fact, I will use some kind of some properties of this inner products, in particular orthogonality and all, for further discussions. Okay. So we say that something is orthogonal, two vectors are orthogonal if their inner product is 0. Just like we say that two vectors on R2 are orthogonal if their dot product is 0. Their angle is pi by 2 between them. So just like that. So now, yeah. Now let me see. We have seen that singular value decomposition is used to compute Moore-Penrose inverse. Now let me come to the most important business here. Why Moore-Penrose inverse is important? Okay. So as I mentioned earlier, this is to solve system of linear equations. So you consider the system of linear equations Ax equal to B. So here A is a m by n matrix, okay, and B is a vector in Cn, and B will be given to you. So such equations will arise naturally from the physical experiments. So when the physical experiments, these systems arise, this B will be known to you. That will be the known parameter, known thing, or the something called the observed quantity or something like that. So B is something known to you, and this equation is formed from some physical experiments. Then at least some part of A will be also known to you. So you assume that A is also known to you. So solving this equation means to find the unknown X with given B and A. That's a solution. So that's what we call a solution. So you need to find an X satisfying this equation. So that's what you call a solution. And keep in your mind that, as all of you know, that in general this equation need not have a solution at all. Okay. There are several problems may arise. The solution need not exist. Solution need not be unique. Even solution may not be computable. Need not be stable. Several issues will come, but Moore-Penrose inverse will be helpful in analyzing the situation. I will tell you one by one. The first thing is that this equation has a solution if and only if A dagger B is a solution. That means you know that, see, suppose A is an invertible square matrix, then what is the solution? A inverse B. So instead of A inverse, you are computing A dagger. So you consider A dagger B. That is this, A dagger B. So you consider A dagger B. The question is whether A dagger B is a solution or not. So this tells you that this equation has a solution if and only if A dagger B is a solution. Okay, I can prove it very easily. Suppose A dagger B is a solution. That means A dagger B equal to B. Then A dagger B is a solution. Therefore, this equation Ax equal to B has a solution. Now the question is, suppose there is a solution Ax equal to B. Then can you say that A dagger B is also a solution? That is easy. So suppose X is a solution to this equation. Then you compute A dagger B. Now B can be replaced by Ax because Ax equal to B. So you write this. Now here you use the property of A dagger, that A dagger A is A itself. So that is Ax. And Ax by assumption is equal to B. So we obtain that A dagger B equal to B. That means A dagger B is a solution. So this system has so the first question is whether a solution exists or not. So using Moore-Penrose inverse, it is easy to verify because you have to check whether A dagger B is a solution or not. If A dagger B is a solution, then there exists a solution. If A dagger B is not a solution, there does not exist any solution. Okay, so that is first thing regarding existence. Now the second thing, suppose solution exists. How about all the solutions? Now here again A dagger B helps you. It tells you that every solution X is something, it will look like this. It will be A dagger B plus something. Okay, and what is that something? That is a kind of projection. So this tells you that every solution X is of the form A dagger B plus I minus A dagger A y for some y. Okay, so this gives you all solutions. Okay, if a solution exists, it gives you all solutions. Let us prove this. So in this proof, I will use some geometric idea of projections, orthogonal projections. If some of you are not comfortable with these orthogonal projections and those direct sum and all, just forget the proof, but keep in your mind that this helps you to compute all the solutions. Okay. Now, this is the thing. Suppose x satisfies ax equal b. You start from an arbitrary solution of ax equal b. You want to prove that x is of this form, right? To prove that x is of this form, what do you have to prove? You want to prove that x minus a dagger b is of this form, I minus a dagger a y. Or in other words, you want to prove that x minus a dagger b is in the range of I minus a dagger a. That's what you have to do. Okay. Yeah. Now we denote this I minus a dagger a by p. And we have already noticed that it's an orthogonal projection. That is very easy. I is an orthogonal projection. So you can just verify that p equal to p square equal to p square. That is from the property of a dagger. So you denote it by p. Now, for an orthogonal projection, this is a very important geometric property. Their null space and range will be orthogonal to each other. So that's why it's called an orthogonal projection. It will project everything as a decom. So it will project onto its range. So its range will be orthogonal to its null space. So this is why it is called an orthogonal projection. So for every element with p square equal to p star equal to p matrix, this is the situation. Null space and range will be orthogonal to each other. Therefore, if you want to show that something is in the range, it suffices to show that it is orthogonal to the null space. Okay. So here you want to prove that it is in the range. I mean, you want to prove that x minus a dagger b is in the range of that. For that, it suffices to prove that x minus a dagger b is orthogonal to the null space. So you start from something in the null space. So you start from set in the null space of p. Set is in the null space of this means I minus a dagger a z equal to 0. And this happens by linear, you just apply this, that means z minus a dagger a z equals 0. That means z is equal to a dagger a z. So you start from something in the null space, say z, so it will satisfy this, z equal to a dagger a z. You want to prove that x minus a dagger b is orthogonal to this. And that will tell you that x minus a dagger b is in the range of this. That's what you are done. So you are going to prove that. So so proving orthogonality it is just like proving that dot product is 0. So here instead of dot product, you will have inner product. That's all. So you look at this inner product. Now what happens that you can replace by a dagger az because of this identity. So it is a dagger az. Now a dagger az can be taken to the first variable with the star. But star will not come here because a dagger a star is a dagger a. So that comes here without any change. So that is the second equation. Now here what happens? You apply linearity. So it is a dagger ax minus a dagger a dagger b, comma z. But now you apply the property here. This a dagger is a dagger itself. So this is a dagger b. And ax equal to b. So this is also a dagger b. So a dagger b minus a dagger b is 0. So 0 inner product with z is 0. So you obtain that this dot product is 0. And that tells you that x minus a dagger b is orthogonal to z for every z in the null space of this thing. Therefore, it is in the range. That means x minus this is in the range. Therefore, you have this decomposition. So this second property tells you that every solution can be written as a combination of a dagger b and something in the range of I minus a dagger a. Now the third question is, what is very special about the solution a dagger b? We already know that if there exists a solution only when a dagger b is a solution. Now what is very special about the solution a dagger b? There may have several solutions. So there may have several solutions, but a dagger b will be the solution with minimal norm. Norm means the Euclidean norm. That means you take any other solution x, then it will satisfy this inequality. Norm of a dagger b will be less than or equal to norm x. That is also very important. So this is a norm. This is a solution with minimal norm. Again, proving we will use some orthogonality. So what we have is this a dagger b, comma I minus a dagger ay. You just do this computation. Let me skip this computation for the time being. So you will prove that a dagger b in dot product with I minus a dagger ay is 0. That means they are orthogonal to each other. So that means you know that every solution will have this property. I mean, has this decomposition. You can write x equal to a dagger b plus I minus a dagger ay. And we proved that they are orthogonal. So this is an orthogonal decomposition of x. Now, just like your basic trigonometry Pythagoras theorem, what happens is that you have a triangle, you treat the sides as vectors, then and see that the hypotenuse is x, and this is obtained as a sum of the other two vectors, and they are orthogonal to each other. So you are having a right angle triangle. So the magnitude of this square plus magnitude of this square will give you the magnitude of this square. Simply the Pythagoras theorem. That's also available in an infinite setting also. So what happens? You obtain norm x square is equal to norm of this square plus norm of this square. Now you see this norm is obtained by adding a non-negative quantity to this norm. Therefore, this should be less than or equal to this. So that's what you have this inequality. So it tells you that you have a solution with a, if you have a solution, a dagger b is the solution of minimal value. Now this property is more important. There are situations where you don't have any solution. Okay, there are also Moore-Penrose inverse is used. So how it can be used? In the situation you don't have any solution, see, this is physically very important. See, for mathematics people, we are always interested to find the solution or to prove that there exists solution and so on. But from the physical phenomena, what happens? They are satisfied with approximate solution also. I mean, they don't need exactly a solution. They need something which behaves like a solution or something which is close to be a solution. Okay, that's enough. They are satisfied with that. In the most of the physical phenomena, that will work. Just like we say that, say, pi is not is equal to 3.14. It is irrational and 3.14 is a rational number and so on. But physically, they are using that. I mean, physical theory, they are using it. So we are always satisfied with the approximate thing. So that is the same thing happening here. Suppose Ax equal to b does not have a solution. Then also this a dagger b will help you. So a dagger b will give you the quantity which is closest to be a solution. In the sense, you call a dagger b equal to x tilde, then you know that ax equal to b, there won't be any x with ax equal to b. The question is the distance from ax and b can be minimized that. So that is minimized by this x tilde. So that means no ax minus b, the distance from ax and b is always greater than or equal to distance from ax tilde and b. That means x tilde line is the closest of being a solution. You don't have any other. This happens for every x. So that means this is why it is called a least square solution. You know that this will not become zero because the system has no solution. So this quantity will not become zero. Therefore, ax tilde will not become equal to b. But this is of minimal norm. I mean, this is the closest point to b. Ax tilde is the closest thing to b. There are no other x which satisfy this. So that is the phenomenon. So in this situation also, we are getting something close to a solution. Again, the proof is very easy. You write ax minus b to be ax minus ax tilde plus ax tilde minus b. And you prove that these two quantities are orthogonal. I mean, ax minus ax tilde is a dagger b because x tilde is that, and this is a dagger. So we prove that these two things are orthogonal, and that will tell you that. So I skip this proof. This is only simple computation. So these are orthogonal to each other. That means again the same Pythagoras theorem will give you that norm of this square will be sum of the norm squares. So norm of ax minus b square is equal to norm of ax minus x tilde square plus this. So you are adding something to obtain this. Therefore, this should be less than or equal to this. That's it. So even when we do not have a solution to this equation, we could obtain some x tilde that is close to being a solution. And that is called a least square solution. Okay. So let me conclude here for the time being. I mean, the application of singular value decomposition to this kind of problems, I mean, solving a system of linear equations and all, is relevant because of this reason, because pseudo inverse or Moore-Penrose inverse is being computed using single value decomposition, and this Moore-Penrose inverse is being used in several physical phenomena to solve a system of linear equation. Now, let me come to an application of single value decomposition to some concrete practical situation. So something very well known, which is known as image compression problem. Yeah. Now, so this is the situation. So if you see my slide, so here I have written 3.75 MP in the color blue. So in fact, there are only 3 colors available in the monitor: red, green, and blue. So here, to make it blue in color, I put the value of red to be 0, green to be 0, and blue to be 1. So that's why it shows something like blue. Now, if I want to make it some color other than red, green, blue, then I have to give some values for some different values for the RGB. So it is known as RGB. So I will put some different values, and what happens? The mixture of these colors, their saturation will trick your brain so that you will feel that it's a different color. But actually, you have only these 3 colors: red, green, and blue. Now, what happens is that suppose you have an image on the screen. How do you see that image? They are stored as small pixels, and each pixels you are giving some value. Okay, so if it is a colored image, you give different values for red, green, and blue in each pixels. Okay, and if you give 0 values, then there won't be anything. But if you give 1, 0, 0, there will be some bluish color. If you give some reddish color, if you give 0, 1, 0, there will be some green color. And a saturation of this will trick your brain so that you will see an image. So if you go zoom, if you zoom it out zoom it in and see, you will see so small pixels. You don't have a continuous image, but small pixels only. Okay. Now they are stored. So an image is stored as pixels. Okay. Now you can. It is in a grid-like pattern. So what happens is that you can see that you can represent it in a matrix form, because each of them are stored in pixels, small pixels. So consider an image of say 100 by 100 pixel in dimension. Then we need 100 by 100 matrix to represent that. Okay. So we have to give values in this 100 by 100 matrix. If you see each pixel as a matrix entry. So that means what? A 100 by 100 pixel in dimension image, you have to put around 10,000 pixel values. I mean, each pixel you have to give this value. And if it is a colored image, this is in the gray image situation. I mean, you have a black and white image. In the black and white image, what happens? You give the same value for red, green, and blue. So that's okay. But if you are giving a color image, then you have to give 3 values. Okay. That means 10,000 into 3, you have to store around 30,000 values in case of a colored image of dimension 100 by 100. Now, in our computers, typical image is of standard definition or high definition image. So that will be of this form. You might have seen this 1280 by 1024 dimension. And this demands 39,32,160 such pixel values. And if you store this into your computer, then it will be around size 3.75 MB. So this creates a huge data issue. Image compression is a big problem because of this. So here comes the role of SPD. So I hope you understood the problem is data compression or image compression. Okay. So now we have an image. We store it in pixels, or you represent it as a matrix. So every matrix is just like representation of an image. Now the question is, can you reduce the size or data which is required or which get to store? Can you reduce the storage size? For that, you need to reduce the size of the matrix. So that is the only way. So can you do that? So that's where SPD comes into picture, or the computation should be reduced. SPD in action. Suppose A denotes a big matrix representing an image. Now you consider the SPD of A. Say UD, U star. You know that this is the SPD. Now you only take the first column of U prime, first column of U, which you denote by U prime, and the first row of V star, which you denote by V star prime. Then A prime, you compute A prime by U prime, D prime, D star prime. D prime means only one entry. So then also you will get a matrix. And this matrix is of the same dimension as A. And this will also represent an image. Okay. So you know that this is a kind of, some portion of A. Okay. Now this will represent an image, and that will be a blurred version of the original image. Okay. Now if you take 2 rows and 2 columns and keep doing this, then you will get a better image, which will not be the original image, but it will be a kind of approximation to that image. And you see the advantage of this is this. See, the number of columns we use to calculate this approximation is, they are called modes. So for example, if you are fixing a level of precision to be 10 modes, then what happens? Instead of 100 by 10 matrix, your original A is a 100 by 10 matrix. You need to U prime is only 100 by 10 matrix. D prime is 10 by 10, and V star prime is 10 by 100. So the total computation or number of pixels we use is only 2,100 pixels instead of 10,000. If it is a colored image, then it is around 6,000 something only instead of 30,000. So this is a reduction which is achieved by single value decomposition. Okay, so I can show you some figures which will give you some clarity. Yeah. Can you see this figure? Can you see this figure? Hello? Hello, can you see this figure?
Yes, sir. Yes, sir. We can see.
Okay. Okay. So you look at the last image, last corner, right corner. This is the original image. Okay. And if you fix a mode of approximation to be 100, you will get the second image, this one. You can see that there is not much difference from the original image. Now again, if you fix it 75, you will attain this image, and 50 modes you will obtain this image, and so on. So finally, if you go lower modes of precision, it will. So this is the first precision. See, just only one mode of precision. So you have a blurred image here. But so here is the problem. So you have to fix which level of precision you require. So if you are satisfied by this kind of precision, then it's fine. So this is a kind of optimization. You need to reduce the usage of data, as well as you need some kind of clarity in the fix. So I can also show you. I can also show you a colored image. So this also has the same thing. So this is the original image. Then you can see that depending on the modes of precision you use, its clarity will be lesser, but data storage will be high. You don't have much data to be used. So this is why single value decomposition is useful in data compression. Now my final topic of application of single value decomposition is known as principal component analysis. So this is a much hotter topic now, and especially now data science is a big very much popular area, and especially we are in a pandemic situation, so everybody is talking about data, and we know that data is something which is used for several interpretations and several conclusions. For example, in the COVID case, so we are not considering all the COVID patients, those who are doing research on the vaccine studies. They are not considering all the COVID patients. Instead, they are taking some samples and taking that data. That is called data, and they are giving some interpretation to their connection or their connection between. So, for example, does there exist a connection of COVID patient? The effect of COVID and the gender, effect of COVID and the climate. So to study all these things, they are only taking some samples and studying, right? So everywhere data is being used. So let me tell you the simplest example, simplest case. So suppose you have a set of data, say x1, x2, xn. For each xi is an d-dimension RD element. That means x1 represent the, so suppose x1, x2, etc. There are some people. X1 represent the, x1 will be a vector. So that means first person's height, weight, say some other features will be listed on the x1. And second person's height, weight, same thing will be listed on x2 and so on. So this is how do you have vectors. So this is the data now. Now, principal component analysis is to identify the patterns in data and understand the variance pattern. That is very important. So you need to understand how the pattern is being formulated, so that from your data itself or from the samples you have taken itself, you can have some conclusion, so that you can prescribe some kind of vaccine or whatever, depending on your study. So this analysis is important for data reduction because often much of the variability of data can be accounted for by a small number of principal components, because data will be collected, there will be big data with you, but you will be analyzing, means much of the data will be need not be useful. So you project it into some principal components in some direction and do the interpretation. That's what we do in practical situation. So PCA can show relationships that were not previously suspected. That is again, see, this is just like your curve fitting. You fit the curve depending on your data and study the situation. That's the idea. I have some definitions here, which is not that important. These are all basic definitions in set probability theory. But I just put it here for the sake of completion. Covariance means, this is the definition, formula for covariance. It actually measures how this x and y vary from the mean. Here is the mean, x bar is here, with respect to each other. So that is what covariance. And variance of x is the deviation from the mean itself. That means covariance of x with x itself, you will have variance. Now, another thing, this is very important. You start from an n by d matrix. There is something called covariant matrix of x. So this is a d by d symmetric matrix. This is found by taking covariance of the columns of this matrix. That's how we work. Now let me just tell you a simple example of linear line fitting. So consider this is my data. Suppose this x, y, z, p, this is the data given to me. And I want to obtain a curve or fit a line such that I need to understand this data. Or from these samples, I need to understand the behavior of this pattern or whatever. So what we actually do, we will actually fit some line here and study about the line. So once you obtain the line, the good fit, then you can understand what will be the behavior at a later time and so on. Now, suppose I am projecting, so I have to project everything on that line, right? Suppose I am projecting everything onto the y-axis here. So then you can see that on the y-axis projection, this x, y, z, they will be close to each other. And p will be also not much different from. So what happens? Your variance will be very small. And you know that this y-axis does not represent this data at all. It is much away from the data, right? So that is the thing you have to keep in your mind. So the variance is small means you have a bad fitting. That is bad. Now, suppose you are fitting on this line. So on this line, you know that they are almost the same. So variance is maximum. They are in their position itself, not much reduced. So here is the maximum variance. So you need to project on the data given to you should be projected onto a line where the variance is maximum. That is the intuition. Okay. So that is how do we introduce principal components. So these are some technical things. So this is the intuition which we use to introduce principal components. For the matrix X with rows Xi, so we compute mu is something called centroid. So let me skip the technical part. So for X minus mu, you have X minus mu here, where mu is the centroid. Centroid can be centroid of the rows. Now, what is the principal component? It is a projection like this, X minus mu acting at B, and such that variance of Y is maximum. So now you know why the variance is maximal from the previous explanation, intuition. So we consider x minus mu acting at some b such that variance is maximal. So now this is the first principal component. Now first principal component is denoted by defined like this, y1, where x minus mu v1 such that variance is maximum. Now how do you define the k principal component, k plus 1 the principal component in the inductive bit? Like if y1, y2, yk are k principal components, then k plus 1 the principal component is defined as yk plus 1 equal to again x minus mu vk plus 1. Again it's a projection such that this variance should be maximized and they should be uncorrelated. That means covariance from others should be 0. And this v1, v2 up to vk plus 1 are called the principal directions. Okay. Again, this is a big area and it makes use of probability theory to some extent. But why do I wanted to introduce this? Singular value decomposition can be used to compute these principal components. So that is where the final application I want to discuss. So SVD yields PCA. So how SVD is helpful here? So X is an n by d matrix of data points with mu being its centroid. Then you compute the SVD of this matrix X minus mu. Suppose SVD is this du d v transpose, where d is this diagonal matrix. So again, we are in the diagonal situation now. So here you have d is this. Okay. So what happens if you know the SVD like this? Then the principal components are obtained like this. See, you take the kth column of UD, I mean the first two things, kth column of UD, and that is what your YK. So this is the kth column of UD, that is the principal components. And kth column of V, that is the principal direction VK. So explicitly you are getting principal components by using SVD. And here variance also can be explicitly computed by this, sigma k square by n minus 1 with all other properties. So single value decomposition lets you compute the principal components explicitly. And this is highly used in the practical scenario. So I think I will summarize this. And as all of you know, this is an era of artificial intelligence, in particular machine learning, data science, and so on. So you have to concentrate on your mathematical background. So mathematical background for these topics include linear algebra, probability theory, and analysis. And of course, you have already seen that singular value decomposition plays a crucial role in such applications. So let me stop here. So these are my references here. This is the algorithm which I mentioned regarding the computation of singular value decomposition. And this is a classical textbook due to Roger A. Horn and C.R. Johnson, matrix analysis. And this is something I used to obtain these figures, which I displayed here, and regarding the image compression and all other things. And recently I did some Coursera courses online. In fact, that was quite helpful. And of course, Wikipedia is a consistent source. Thank you very much. I hope I'll be attending some questions, right? Yeah.
Thank you, sir. In the chat box, there is a question. Why the null space of pseudo inverse equals the null space of the matrix transpose?
So what is the question? Why the null space of the
Pseudo inverse. Null space of pseudo inverse equals the null space of the matrix transpose.
Oh, that's not the way. Oh. Null space of the pseudo inverse. No.
Okay, sir.
I think the question will be the other one. I mean, null space. Why the null space is perpendicular to the range? That's what. Isn't it?
And that is basically linear algebra.
Yeah, that is basically algebra. But the other thing I don't.
Okay. Sir, is there any algorithm to find a Moore-Penrose inverse of a matrix?
Yeah, plenty. I mean, that's what I mentioned in the end. I mean,
okay.
Yeah. You look at this reference, Gulab. So there are plenty of algorithms to find SVD. And this is one of the classical algorithm. And there are several modifications of this algorithm. This is due to Gulab, RH, and Range C. So there are modifications due to Tony Chan and other people. And if you are able to compute singular value decomposition, then definitely by the formula which I mentioned, you can compute the Moore-Penrose inverse. You may refer to that, right? So that's what we have. So directly you have compute. That is the advantage of single value decomposition. This algorithm is available already to compute single value decomposition. Therefore, you can directly compute Moore-Penrose inverse.
Okay, so one more question. From Moore-Penrose inverse, can we find out the matrix A? From A dagger, can we find out A?
I'm not sure. So the thing is that from A inverse, you can compute A, right? But this is definitely, yeah, yes. So because A dagger is unique, yeah. So in principle, it is possible because corresponding to A, you have a unique A dagger, right? So in principle, it is possible. It should be. I don't know. I'm not sure.
Theoretically, it is possible, but given any Moore-Penrose inverse, can we find out the basic matrix A? Is there any algorithm?
No, I guess their question will be A dagger gives you A. That is the question, right? You take dagger of A. I think it's algebraic, right? A dagger is A. That is their question, right? Is it?
That comes as a part of this question.
I think you have to work out. I don't know.
Okay, sir. So one more question. Does x dagger x minus 1 minus I always exist? Anandu, you can unmute yourself and ask.
Please. So I'm unable to see the slides. See, I'm unable to stop sharing. How do I stop sharing? Okay. I stop. Yeah, now you can ask me questions. Please.
Anandu, can you unmute yourself? There is a message there in the chat box. Does x dagger
okay, I can see this.
Okay.
X prime x minus 1. But it's not clear. Is it x dagger? Is it x dagger x? Does x dagger x? Is it x dagger?
Anandu, can you unmute yourself?
This is Anand. This is Naveen.
Yeah, Anandu and Naveen. The same question asked.
Can they ask this? I mean,
Sijan sir, are they unmuted or?
I have sent one notification to them, but they are not responding.
Okay.
They can ask actually. I mean, it's not clear. What? I mean, x prime x. Is it x dagger?
Maybe x dagger x minus I.
No, but what they mean by always exists? Or it is not clear. If they ask the question, that would be fair, I think.
They are not responding for the notification for unmuting.
Okay.
Okay.
That means.
So the question is, does x dagger x the whole inverse always exist?
Okay. This is all inverse, right? Okay. So that is not correct. I mean, your question is whether x dagger x all inverse exists, right? In fact, x dagger x is only that may not be the case because x dagger x is a projection only. Okay, orthogonal projection, and an orthogonal projection, unless the trivial cases, need not be invertible. Okay, its null space will be non-trivial, except for the trivial cases. So the inverse need not exist. Inverse need not exist. Is that clear to you?
Yes, sir. Clear. The net was a bit slow. Sorry.
Okay. That's fine. In fact, it's an orthogonal projection. Okay. So then what happens that orthogonal projection, unless it is identity or identity, what happens that it will have a non-trivial null space. That itself makes it non-invertible. That's the problem. Yeah. Yeah, I got your
Okay.
question now. Yeah.
Thank you, sir.
Participants, any more queries?
However, you had another question. Oh, 1 second. The first person asked another question, right? Why the null space of pseudo inverse equals the null space of matrix and transpose?
We discussed. The question was not clear to us.
Yeah, but this is the same person, right? He can ask it now.
Yes, he's the same person.
Let him ask this question. Naveen, this is Naveen.
Yes, Naveen.
Sir, the null space of pseudo inverse always equals.
Why do you think so?
Sir, before the seminar, when I went through singular value decomposition, I found such a question.
Okay. I have to work it out. I mean, I'm not sure. Immediately, I don't have an answer. I thought I
Okay.
used it somewhere, so I did not use it. Right?
Okay, sir.
Okay.
Thank you, sir. I think we can wind up now.
Okay.
So,
Yeah.
so
Okay.
finally,
Thank you.
I invite Professor Sindhu V, Assistant Professor of our college, to propose vote of thanks.
Thank you. A very good evening to all. It gives me an immense pleasure to deliver the vote of thanks for the webinar to all the dignitaries and participants assembled here. On behalf of our mathematics department, I would like to thank our resource person, Dr. V.B. Kiran Kumar, Assistant Professor, Department of Mathematics, QSAT, who honored this function with his valuable topic SVD. It was very, very informative session, newly especially. Thanks a lot for your time and the seminar, sir. In future too, we expect similar informative classes from you, sir. It also adds happiness to know that Kiran sir was a PG mate for our analyst at QSAT. I hope you also had a nice experience. Well,
Yeah. Yeah, definitely. It was a pleasure discussing it. Except for the fact that we are unable to interact much directly. It was a pleasure discussing this.
our
Thank you
pleasure.
once again. Thank you all colleagues of ANN also. Let me thank all.
Next, on behalf of our maths department, I extend our sincere thanks to our Reverend Manager, Father Anil Jose, Pro Manager Father Abhilash, respected supportive principal Dr. Vincent B. Netto, and energetic vice principals Mrs. Greta Ildefons and Dr. M.R. Shelley. I also extend my sincere thanks to our respected HOD, Mrs. Sylvia Anthony, dear colleagues, Mrs. Anne Varghese, Dr. Roshni B., and all the other dear faculty members of our department whose endeavors result was this webinar. I also extend sincere thanks to our IQSC coordinator, Dr. Shaiju PN, and all the IQSC team members for the grand success of the webinar. Lastly, not leastly, on behalf of Maths Department, I extend my sincere thanks to all the student participants of Fatima and students and faculty members from other institutions for making this webinar a grand success. We hope that today's topic is fruitful and understandable and give you further insight in the topic. Once again, I thank one and all present here cordially. Thank you.
Thank you, Sindhu. Thank you, Kiran sir. Thank you, Sijin sir, on behalf of IQAC. And thank you all, dear participants. The meeting is dispersed. One more thing, the feedback link is given in the chat box. Participants, you please fill up the form. You will receive participation certificate in your mail ID.